This conference will now be recorded.
Okay. Please carry on. Thank you. Right.
And then this is the IEEE spectrum band. Instead of electrical and electronic engineering, we can take from a microwave spectrum bands, whatever the bands were operated here, using of our waveguides analysis or any microwave tube analysis. And for that case, we take from the starting frequency, we take from high frequency, and this is considered in the form of gigahertz frequency from 0.003 to 0.030 gigahertz. Next, VHF, very high frequency, ultra high frequency. But here, this spectrum we are using from L band to up to this one for our microwave analysis. And starting from 1 to 2 gigahertz to up to maximum, we are using of greater than 3 gigahertz, depending upon the application. And for that case, the frequency ranges are varying from L to L band, S band, C band, X band, Ku band, K band, and whatever the application. Suppose we take, I take a C band application. This is for design for radar application, and I take for this X band means you take the application for 8 to 12 gigahertz. This is for satellite design. And next you can take for suppose 2 to 4. Within this, we are designing for some Bluetooth application or Wi-Fi application, double LAN application of Ethernets. All are designed within that frequencies. The next, coming to next one is advantages of microwaves, where we are using of our microwaves in our real-time applications in our day-by-day life, where we can observe for the use of microwaves when operating at 1 gigahertz to 1000 gigahertz. And first one we can take for increased bandwidth availability. And here, compared to our previous systems of what we learned for our communication system, by using of these microwaves, we can increase the bandwidth of the system for dual operations or multiple operations. For suppose we take for our antenna analysis, I'm using suppose I'm designing a one antenna, and this antenna can be applicable to multiple application and single application. Suppose I am designing of that antenna only for Wi-Fi application, and this is operated at 2.5 gigahertz or 5.8 gigahertz. Suppose for the same antenna I want to implement for a multiple application, means it is used for a WLAN application, and this is used for Wi-Fi application, and this is used for Bluetooth application, or this is also used for radar application, and this is also used for satellite application. And for that case, what about the antenna I am designing, and that antenna we are taking in the form of a multiple output. We can take in the form of a multiple operation. And what about these multiple operations means, what are the different applications I considered for a single antenna used for multiple application. For all the cases, I want to resonate of my frequency, whatever the frequencies the applications are required. For that case, we observed for our we considered as a microstrip antenna, suppose, and these microstrip antennas are taken in the form of narrow bandwidth as well as wide bandwidth. But most of the case, these microstrip antennas are useful for narrow bandwidth. But suppose I want to design for the multiple antenna for bandwidth availability, for we go for ultra wideband system. This ultra wideband means we take from the frequency 3.1 gigahertz to 10.6 gigahertz, and within that frequency we are using for multiple operation. For that case, this is one of the advantages of increased bandwidth availability is possible by using of our microwaves. Next, the second one is improved directivity properties, and this improved directivity properties means we take from directivity means the ratio of maximum radiation intensity to the average radiation intensity of your device. And when we are using of compared to previous devices, I am using at microwave frequency where improve our directivity properties compared to the previous frequencies of VHF frequency, UHF frequency, and basic frequencies of VLF, low frequency, medium frequency, high frequencies. And then next you can take from fading effect and reliability, and this is also one of the important criteria for when we are designing of our devices, microwave devices. We can check the effect of fading, whether it is a loss of the system or not, when it about its reliability. And next, another advantage is the power requirement, but compared to our previous devices, we are using of our waveguide to operate of that frequency is required less power. And next, another one is transparency property of microwaves, and this is for the traveling of our data from the different types of application. We can maintain the transparency also is very good for using of these microwaves. And then coming to the application areas where we are using of these of microwaves, we take a first application is telecommunication, and this telecommunication we are using for our telephone, television, and space communication. And this space communication will take greater than 2 megahertz for ground wave propagation, sky wave propagation, and these are all the cases we are propagated. And next, using for radars, and using of radar means when we are designing one radar in the form of CW radar, FMCW radar, or MTI radar like this, and for all the cases we can detect aircrafts, the track and guide of missiles, and air traffic control. These are all controlled by using of design of radar operated at microwave frequencies. And then next we can observe some of the applications of commercial and industrial use. But what we observed in our society, the real-time application we observed in our day-by-day life. And one of the example is commercial application. Can take a microwave ovens, and for textile industries, food and paper industry, and clothing industry, and manufacturing of printed matters, food processing industry, and rubber industry. And next, another nowadays we are using the important application for our using of our microwaves is electronic warfare, and this is nothing about ECM/ECCM, means electronic countermeasures and electronic countermeasures. And this is the present we are using for what about the problems we are facing for towers. We are producing as a lot of radiation. The increasing of mobile phones in our society, it creates a lot of radiation from cell towers, and these cell towers radiations can be controlled by using the technique of some of the methods of ECM and ECCM techniques. And by using of that techniques, how can we can control even though we are operated at gigahertz frequency, this is very harmful to our human being size. You can't see that gigahertz frequency, and that can be controlled by using of some of the technique of this ECM and ECCM technique, and also used for our spectrum. Next, another application for our microwaves is identifying objects or personal by non-contact methods, and these are all some of the application areas. But up to now, we can observe the first part of our first unit. What about the micro spectrum and bands, advantages and application? And we can expect from this one question either in part A or part B. From this unit, they can asking what are the applications of microwaves, or draw the frequency spectrum of microwave. But we can expect from this either a part A question or part B. Just we can list out, we cannot written all explanation. Just what about the applications is there, they can asking any 3 or 4. Just you can read out any 5 or 6 you learn, and from this they can asking any 2 or 3, write that one. And we can expect from part A. And next we move to the second part of this unit is waveguides. And I know we know already the waveguides are classified into 3 different types: parallel plane wave, rectangular waveguide, and circular waveguide. But we start with, according to our syllabus, with rectangular waveguides. But first, why we go for waveguide? Already I told this point. At microwave frequencies, means the range of frequencies 1 gigahertz to 1000 gigahertz, and within the frequency range, transmission of electromagnetic energy along the transmission lines and coaxial cables becomes very difficult. But the previous case of our subject we take from our transmission electromagnetic wave and transmission lines, whatever we are operated, these are all the devices we are using. The medium is coaxial cables. And these coaxial cables has a maximum transmit the information up to 1 gigahertz. But the frequency is greater than 1 gigahertz. There is no possibility for the coaxial cables transmit of that frequencies. But what we have to observe when even though I want to transmit at that frequency in coaxial cables, what are the problems we are facing is, the first one is dielectric losses, and second one is conductor losses or skin effect losses. Means what about the electromagnetic signal we are propagated in that coaxial cable? That electromagnetic signal has a frequency greater than 1 gigahertz. It is not transmitted properly by using of coaxial cables. We observe dielectric loss and conductor loss. It means whatever the information I want to transmit from sender to receiver, either in free space or anything, and this data is not transmitted properly at the receiver side. And why the data is not proper means this device, the coaxial cable device, has not the capability to transmit of that particular information. where even though we are transmitted that information, we got a problem of these losses. Means the loss means whatever the information you are sending at the transmitter, and this is not goes to properly at the output side. That's why the other side, whatever the person is there, is not gathering of whatever the information you are sending at the transmitter. That's why this is the main big problem for why we go for our waveguides. And then we can observe here waveguide, and this waveguide means a rectangular waveguide here I am using. These are all the different types of shapes. And you take a rectangular waveguide. Rectangular means we are measuring in the form of what about its breadth and width of the waveguide. And this rectangular waveguide has analyzed by using of the coordinate system of rectangular coordinate system. But we know our entire electromagnetic analysis can be analyzed by using of three types of coordinate system. But we are learning on our basic secondary level. And that case, rectangular coordinate system, circular or cylindrical coordinate system, and spherical coordinate system. And we know already the spherical coordinate system are already analyzed by using of our entire antenna analysis is done by using of spherical coordinate system by using the components of r, theta, and phi. And we go for rectangular coordinate system. The entire analysis is done by rectangular coordinate system x, y, and z. And we go for circular waveguide. Circular means is in the form of a circular shape, and this circular shape means we are measuring the any circular shape of dimensions are in terms of radius. What about the radius of that circular device? And that's why this is taken in the form of a circular, cylindrical or circular type of waveguide. And this circular or cylindrical type of waveguide can be analyzed by using of cylindrical coordinate system. And the cylindrical coordinate systems are rho, phi, and z. These are the analyzing parameters for how we take for our devices. And then how we are manufactured, what are the metals required to manufacture to protect off our waveguide, even though we are transmitting high frequencies of 1 gigahertz to 1000 gigahertz. That much amount of high frequencies can be transmitted by using of waveguide. How the capability to protect means these waveguides are manufactured with the materials of copper, aluminum, or brass. And by using of these type of materials, it can protect easily of our waveguide, even though we are transmitting at a microwave frequency. And then this is types of waveguides. And then next, this is the basic waveguides are why we are taking only rectangular shape and circular shape for waveguides. But we have in our nature so many types of shapes is there. But we have so many type of shapes is there, but we consider for all type of shapes in the form of elliptical, single rigid type, double rigid type, or any type. But whenever we are transmitting of the electromagnetic wave in any type of waveguide, we must analyze. But the analyzation of the waveguide is easily possible only for regular shapes only. But we consider irregular shapes, the analyzation is very difficult. That's why most of the cases our waveguide analysis are analyzed with rectangular shape and circular shapes. But you take another shapes of what I write here, elliptical shape, single rigid type, double rigid type. This is already we draw in our notes also in the concept of types of waveguides, what is the shapes. But the problem with these shapes is you transmit the electromagnetic wave, there is no problem, but the analysis, but we go for the electromagnetic waves, we are using either antenna or a waveguide or using radar or satellite, the analyzation is very important. And without analyzation, what about the mathematical expressions we are developing for these electromagnetic analysis, we can't say whether it is correct or not. But we using of these rectangular and circular waveguides, it is very easy to analyzing the components how we are designed. But we go for that one, the analyze we can, there's a possibility is there, but analyzation is very difficult. That's why I'm not going this one. And this is the exact definition. What is meant by waveguide? A hollow metallic tube of uniform cross section for transmitting of electromagnetic waves for successive reflections from the tube. Next, we go for this is the basic shapes. And rectangular means you take along x-axis is breadth, we can represent with A, along y-axis with B, and you take for circular waveguide, we what about the radius of the circular from center point, and I take with the A. And then we go for our concept of propagation of electromagnetic waves in rectangular waveguides. But you know, for rectangular waveguide, and this rectangular waveguide has rectangular means 4 sides, and according to our system, we can call as 4 walls of the waveguide. One is bottom side, top side, left side, and bottom side. And how the electromagnetic wave is propagated within the rectangular waveguide, we have to analyze by using of this propagation, transverse electric waves separately, transverse magnetic waves separately, and transverse electromagnetic waves separately. First, I go with what is meant by TEM, transverse electric and magnetic waves. The propagation of transverse and electric and magnetic waves means here both field components are present. When both field components are present means the field components of EZ and HZ. The electric field along Z direction, the magnetic field along Z direction, both are equal to 0. But why I take this Z means our rectangular waveguide are analyzed by using of rectangular coordinate system of X, Y, Z. But here you can take for electric field components of EX, EY, EZ, magnetic field components of HX, HY, HZ. When we take of TEM wave means both electric and magnetic fields are present, the components of EZ and HZ equal to 0. And then next you take for second case, this is a transverse electric waves, and this transverse electric waves means the electric field along the Z direction and this component equal to 0, and magnetic field along Z component is different from 0. Next, transverse magnetic waves, the magnetic field is present along Z direction, and in case that HZ equal to 0 and the value of EZ is different from 0. For this entire analysis, we are using of a rectangular waveguide. We have to analyze what about the field components of EX, EY, EZ, HX, HY, and HZ. And then this is what we are observed for the previous case, same thing. And next, this is the analysis process for TE, TM, and TEM waves in rectangular waveguide. How we are analyzing of all those things. And we go for first step is find out all the field components EX, EY, EZ, EX, EY, HX, HY for transverse electric waves and transverse magnetic waves using rectangular coordinate system. And then next we are calculating the Z component using the second step depending upon the transverse wave in EZ and HZ components by using of separation of variable method. Means we write already in our notes EZ is equal to XY. And this X is taken as A cos 1 Bx, A1 cos 1 Bx, A2 sin Bx, and B1 cos B1 sin Bx, B2 sin Bx. And next using boundary conditions, and this boundary condition means the rectangular waveguides has 4 sides, right side wall, left side wall, top wall, and bottom wall. And using all the boundary conditions, we are evaluating field components. And these are all the designing steps, analyzing of how to find the field components. And this is we can observe. First, I take for solution of TM waves. Solution of wave equations for transverse electric waves. We got the components of EZ, EX, EY, HX, HY. The propagation of transverse electromagnetic waves means the field component along HZ equal to 0. We got remaining all components. And this is the general expression. Only transverse magnetic waves means we got the sign terms where C is constant. And this is sin m pi by x, sin n pi by b into y, y into y, and e power j omega t into minus gamma z. And this is the direction of wave. The resultant wave is propagating along the z direction. And this is sin m pi. This is the length. A means our along length side we represent with parameter of a, and b means we are representing which side. Means y-axis. Along x-axis we take as a, along y-axis we take as b. And this is total field component of Ez. And next, these EX, EY, HX, HY, and HZ, these are all calculated by using of our field equation solutions. We can show already we observed in our class how we done one by one steps. And this is already we observed in propagation of waves. First, we take a coordinate system along x-axis means breadth and width waveguide, and using of wave equations for TE wave and TM wave, and expanding rectangular coordinate system. Already I am telling. This is a rectangular coordinate system of dou square Ez by dou x square, dou square Ez by dou y square, dou square Ez by dou z square. And next using of separation of variable method, by solving above all the using Maxwell's equation, we can solve all the field components. These are all your entire class notes is there. we can already observe in our classroom how we can solve the field components. That I am taking directly all the field components. Directly we got this EX, EY, HX, HY and EZ components. And next we go for similarly for TE waves. Again, TE waves means EZ is equal to 0 and HZ is different from 0. Again, you take all whatever field components is there, EX, EY, HX, HY. From this, we are calculating the magnetic field along Z direction. But previous case, you take electric field, we got both are sine components, sine m pi by x, sine n pi by b along the Z direction. And this case, we observed for transverse electric waves, we got a cos components. But entire analysis is same, but need not to go for a difficulty. Again, we can solve all this equation. Whatever the procedure we follow for the first case, the step-by-step analysis, what I am saying here, step 1, step 2, step 3, step 4. But you go for one by one step, we got our final components. But both the case of TE as well as TM, again, we got the same components, but you observe for TM, it becomes sine components. You observe for T, it becomes as cos components. And again, these components are easily to identify. Some of the modification what we done in EX, EY, HX, HY in our TM waves, and a little bit change in here. But this is already we can observe in our classroom how we can change it. Here constant is in terms of gamma by h square. These are reverse for EX and EY. The constants is minus gamma by h square minus gamma by h square. And coming to here, EX and EY is reverse, but those are belongs to the gamma by h square and minus gamma by h square for HX and HY. But we can replica of this one when we take from transverse electric and transverse magnetic waves. The field components are different, but we can write for easily by taking from TM the reverse values of this one. Next, coming to the waveguides, this is the analysis is completed. Next, how can we say your waveguide is good or bad? Means this is based on our parameters, what I say already in starting of our topic. And this is first what is meant by mode. And this mode means it represents what about the value of its either transverse electric or transverse magnetic wave inside the waveguide. And dominant mode means we are operated with the number of modes. Dominant means which has highest cutoff wavelength and lowest cutoff frequency. The mode which has highest cutoff wavelength and lowest cutoff frequency is called as a dominant mode. And how we can solve this observed later. And next parameter is guide wavelength. What is meant by guide wavelength? It is denoted by the symbol lambda g. This is already observed in notes. It is defined as distance traveled by the wave to undergo a phase shift of 2 pi radians. And this is called guide wavelength. Next, we know the guide wavelength. We can find out the phase velocity, and it is defined as the rate at which how much amount the wave is propagated in our system. Next, group velocity, the rate at which. Rate means we are taking the differentiation function of our expression. Next, what about the degenerative means which frequency, cutoff frequency have same cutoff frequency values is there. Means suppose TE01, TE10, and these are all called degenerative modes. And next we can take for this case, after analyzing of all these, we got a component of first we are evaluating the cutoff frequency. And this cutoff frequency means C by 2 pi, and C means we written as 1 by square root of mu epsilon, and this is velocity of light 3 into 10 power 8 meter per second. The cutoff frequency should be equal 1 by 2 pi square root of m pi by a whole square plus n pi by b whole square, where m and n are the modes of operation for both transverse electric and transverse magnetic waves, and where a and b are the breadth and width of the your rectangular waveguide. And then similarly for calculating for transverse magnetic modes also, we got the same expression C by 2, and we got a square root of m by a whole square plus n by b whole square. And this is already we observed in our classroom how we can derive of this expression. And next here I am writing take for suppose TE rectangular waveguide. For TE mode, the dominant mode is TE10. For TM modes, the dominant mode is TM11. How can we say this is a dominant mode? Means according to I told previously one of the definition which has highest cutoff wavelength and lowest cutoff frequency. When the general expression for cutoff wavelength is lambda c is equal to 2ab by square root of m square b square plus n square a square. Suppose we take T is equal 1 and 2, where the value of m is equal 1 and n is equal to we can substitute here. When we are varying of the different types of values, we got T10 has a highest value, means we got lambda c is equal to AB by square root of m square b square plus n square a square, where m and n means 1 and 0. And we got the expression 2ab by a after substituting m is equal to 1 and n is equal to 0. And from this relation, we got lambda c is equal to a, and 2a means our 1, and that we can become as T10 is the dominant mode for T waves. Similarly, we take for TM modes, and this will become as TM11. And the next parameter is wave impedance. The definition of wave impedance means the ratio of strength of electric field in one transverse direction to the strength of magnetic field in another transverse direction. The strength of electric field in x direction, strength of magnetic field in y direction. But if you take in reverse case, it will become as a negative sign minus Ey by hx. I'm telling later the equations. And this is the general expression what we take from phase constant, intrinsic impedance. You know, this is the general expressions. Next, for intrinsic impedance for TM waves, I got eta naught into square root of 1 minus fc by f. This is cutoff frequency, and this is your frequency. For TE waves, it become 1 by this function eta naught by square root of 1 minus fc by f whole square, and intrinsic impedance should be equal to 125 ohms. But these are all the parameters. We can expect one essay question from these waveguide parameters. We can given a problem like this. For a rectangular waveguide, have a dimensions of 7.5 by 3 centimeters. 7.5 by 3 centimeters. It is operated with a dominant mode. Find the parameters of cutoff wavelength, guided wavelength, phase velocity, group velocity, and its wave impedance. And I'm asking the question like this. We can expect 100% of this question from this unit, either essay questions from A bit or B bit. Maximum we can expect from A bit is from solutions. What we observed for previous case, solution of TE waves, solution of TM waves. Definitely we got one question, and another question, another essay question from parameter analysis, and they can given a problem. And for this problem, we can solve what I am saying the problem for 7 centimeters by 3.5 centimeters means A and B, and using of these mathematical equation direct, these are all direct equations. Just you can substitute whatever the values is there, and that equations we got all the values. And this related to waveguide parameters, how we can observe all these phase velocity, group velocity. And I can take, this is one of the example, a problem taken from our standard textbook Leo. We can given a rectangular waveguide whose dimensions is given, and for that dimensions I am calculating for T10 mode. The cutoff frequency is 6.561 gigahertz, and this is for the mode of T01 mode. And for the mode T0 mode, and I am calculating the cutoff frequency by using the formula of Fc is equal to c by 2 square root of m by a whole square plus n by b whole square, and the values of a and b is given in the problem. And for that case, we got the cutoff frequency. For this case, we are telling from which one is a dominant mode or depending upon our expressions. But definitely, we got one essay question from a solution of equations what we observed for previously Ex, Ey, Ez, Hx, Hy, Hz. And similarly, for these waveguide parameters, you got a problem, or sometimes they can ask the mathematical expressions. And come to the last part, power transmission in rectangular waveguide. And this, you know already, power means in our basic electromagnetic analysis, we observed power is calculated according to Poynting theorem. I am using the same Poynting theorem expression 1 by 2 into E cross H, and I am calculating for electric field for TM Mn modes and magnetic fields TE Mn modes, and the power transmission expression will become this one. 1 by 2 eta means intrinsic impedance, lambda naught is a free space, and lambda c is your cutoff wavelength. This cutoff wavelength is for rectangular waveguide. The expression is 2ab by square root of m square b square plus n square a square. From this relation we are calculating, and these are the dimensions. This is along electric field, along x direction, along y direction. Similarly for transverse electric waves, again using the expression. This is a power transmission means how much amount of power is transmitted. How much amount of power is transmitted to your rectangular waveguide. This is easily to identify by using of this mathematical equation. How much amount of power I am transmitted in my waveguide. And next one is losses. Means suppose I am giving a for that rectangular waveguide 150 watts of power, but it reached to output side we got the same 150 watts power or only 75 watt power or 100 watt power or 0 watt power. How can we can estimate means, and this can be find out in the form of losses. And I'm giving a 150 watt of power, and this 150 watt of power is receiving at the output side or not. We can check by using of these power losses. And these losses can be calculated by using of dielectric. Already we told for what we are using for the losses in dielectric and losses in the waveguide. And losses in dielectric means you are using for the starting frequency. Losses in the waveguide means your rectangular waveguide. And we can is also you take for propagation of TE modes. We are calculating by using of this analysis. We are propagating of TM modes by using of this analysis. And this is power losses and power. And this is one of the real-time example how we are designing in a software. I will tell this at the end of third units. You can have a time is there how we are implementing this in a real-time softwares by using of CST softwares or ADS softwares of electromagnetic RF frequency software. So whatever I am saying in up to now in theoretical part, but this is entire three-dimensional view we can't see. That's why we go for the softwares. We can easily to analyze how the distribution of electric field, how the distribution of magnetic field is easily analyzed by using of this software. I will tell you later if you have a time is there. And next we move to our second unit, circular waveguide. Once you know the first unit completely, the second unit is very easy. Once you know what we observed up to now, the first entire unit of our rectangular waveguides we can observe. And the same thing we are going to discuss in our circular waveguide, but the only difference is coordinate system. This is already I told. For rectangular waveguides are operated with rectangular coordinate system, and circular waveguides are operated with the circular or cylindrical coordinate system. And the circular or cylindrical coordinate system means we are analyzing our same electromagnetic wave by using the field components of cylindrical field components of rho, phi and z. And again we want to analyze when the electromagnetic wave is propagating in circular type of waveguide, circular shape of waveguide. When we are propagating circular shape of waveguide, how we are analyzing. But previously what we done, entire thing will be done in rectangular shape. And now that case, what about the components we are calculated, same thing we can observe here. But coming to here, using of circular waveguide, how the distribution is done and how we find out the field components, and again waveguide parameters. For that case, we go for our circular waveguide. The entire analysis is done by using our cylindrical coordinate system of rho, phi, z. For that case, we are going to evaluate the parameter of E rho, E phi, Ez, H rho, H phi, Hz. And these are all the field components we are going to evaluate. And for that case, we go with the first slide. And these are all the contents given in our syllabus. The characters equation, dominant and degenerate modes. Again, same concepts. What about rectangular and circular cavities? And next, coupling coefficient, excitation techniques. And then additionally, we are adding here two types in the form of, one is cavity resonators, and the second one is in the form of the extension of our microstrip lines, what we learn our antennas. And this is related to waveguide, how we can extend. We can observe the last two parts. The first two parts are already same what we observed for the previous case. Next, coming to this is the component of circular waveguide. Again, this is a circular shape, and this is the center point. And we can draw our XYZ analysis are converted into rho phi z analysis. But we know for we are learning in our basic electromagnetic analysis how we convert one type of coordinate system into another type of coordinate system, rectangular to cylindrical coordinate system or cylindrical to rectangular coordinate system. We know, but here I take the basic components are XYZ, and these are converted into circular cylindrical coordinate system in the form of rho phi z. And for that case, you take along the x and y, we take a components of rho, and z, there is no change in z, and we take a phi between here, phi. And next, here I take along z axis. And here, what about the components we take here? The circular waveguide is basically a tube or circular conductor. Here the phi means this one, and this is varies from 0 to 2 pi values. And rho means be in between x and y, and this is varies from 0 to a, means this is a radius. And L means along Z axis I am taking what about the length of the conductor, and this length of the conductor I am taking along Z axis. And next, how we solve these circular waveguide equations? We go for using Helmholtz wave equations for TE waves, again TM waves in Z direction. The basic components of del square Hz is equal to 0 and del square Ez is equal to 0. And this del square Hz means for rectangular coordinate system we can expand dou square Hz by dou x square, dou square Hz by dou y square, dou square Hz by dou z square, which is equal to minus omega square mu epsilon into Hz. This is for rectangular. But here we are analyzing circular waveguide. Your expression can be changed in the form of dou square Hz by dou rho square plus 1 by rho into dou square Hz by dou phi square plus 1 by sin rho sin theta into dou square Hz by dou z square. But we can take, I will show in our components. For operate for TE waves, Ez equal to 0, again Hz is different from 0. We are using of this Helmholtz equation. We can solve the field components of H rho, H phi, Hz. For TM waves, again we are solving the components of E rho, E phi, Ez, H rho, H phi, Hz. Again same concept, but the coordinate system is only different. And next, again same steps. What I write for the previous cases, but that case we can observe the components in terms Ex, Ey, Hx, Hy. But I am changing the coordinate system for circular waveguide E rho, E phi, H rho, H phi. Again, there is no change in Z direction. Again, Ez, Hz components. But again, we are applying boundary condition after solving the value of electric field along Z direction, magnetic field along the Z direction. For that components, we got I think Ez is equal to C naught cos n phi. E power some function, and similarly for Hz is equal to C naught of rho into some sine function and e power some function, exponential function. Again, using of your equations, Helmholtz equations, we can put our all equations are solved using of Ez and Hz. Finally, we can evaluate the field components of E rho, E phi, Ez, similarly H rho, H phi, Hz. But only the coordinate system is different, analysis is same. For that case, I got these are all the expression values. For E rho, C naught of rho, this is constant, but we are going to analyzing of our entire boundary conditions for cylindrical coordinate system by using Bessel function. But you know the Bessel function we are already using in our analog communication system for to find out the frequency modulation. But here, what about the my separation of variable expression is there for circular waveguides in terms of circular coordinate system of rho phi z. These analyses are done by using of Bessel function. I will show in our inside equations. That's why where Jn of x means this is a Bessel function Jn of rho h, and this rho means your radius a. One is for a sine component, one for cos component, and similarly for E rho, E phi, Ez, H rho, H phi, Hz. Again, we can solve this one by using of our equations. This is already done in our class notes. You draw your circular waveguide and you take your propagation of wave equations for Maxwell's equation, and what I am saying, expansion of your circular coordinate system dou square Hz by dou rho square, 1 by rho dou Hz by dou rho, 1 by rho square dou Hz by dou rho square. Again, using a partial differential equation of separation of variable method, and you can solve your entire equations by using Bessel function. And using this is the Bessel function form. We got rho h square. This is general Bessel function equation: x square d square by dou x square, x into dy by dx square. And our expression is our circular coordinate system expression in Bessel form. And we can solve in Bessel equation. We got the final solution. And these are all the equations using boundary condition substitution. And this is Bessel function table. This is already provided for the scientist. Suppose you take TE mode, TM mode. Suppose TE 2,3 means you go for m is equal to n is equal to 3. The value of 2,3 should be equal to 8.015. This is table provided by the scientist. We can table. But our rectangular waveguide we can solve with the help of mathematical equation. Lambda c is equal to ab by square root of m square b square plus n square a square. But coming to circular waveguide, the expressions are in terms of Bessel, and the Bessel function is table is there, but you got the mode TE23 or TE32 from the table only we can directly take in. And from the table also we can take what is meant by dominant mode, what is meant by degenerative mode, means which has lowest cutoff wavelength. Means here we can observe the entire table 3 point, 7 point, 10 point, like this. Here we can observe T 1.841, and this is the lowest value, and this is M and N mode TE11, or suppose you take for transverse magnetic, this is for TM11. This is how can we say dominant mode of all those things. And this is our final solutions. These are all already we have solved in classroom, how we can solve all those things. Just I am showing of how to got the expression for TE waves. Similarly, TM waves we can solve. This is a table for TM waves, but here also we can observe the what is the lowest value for TM waves. This is 2.405, and this is the TM10 mode is the dominant mode. For circular waveguides for TM10 mode, directly we can say from the table, and these are all the solution of equations. Again, same parameters, cutoff wavelength. Again, that one. This is for solution TE and solution for TM, and this is the expression for cutoff wavelength. Same what we go for previous case, and the expression for cutoff wavelength for rectangular waveguide is what I am saying, 2ab by square root of m square b square plus n square a square. This is rectangular. The dimensions are a and b. But our circular waveguide only we have take one dimension in the form of radius. How much amount of radius of your circular waveguide? And this radius of waveguide means a. I am representing. That case we write the cutoff wavelength expression is for TE waves, lambda c is equal to 2 pi by h. 2 pi by h means p dash n m by a, and this we got from our mathematical equation, and this value we are taking from our table. What I already show for 2 pi a by p dash n m, and from the table I observed, already I am writing from the table I observed 1.841. I show the table from n is equal to 1, m is equal to 1, hence in circular waveguide TE11 is the dominant mode. And similarly for TM waves, and cutoff wavelength expression is 2 pi by h p dash n m by a, and this case we can take 2 pi a by nm, and here according to table we can take approximately 2 point something value, and this is called the dominant mode for TE11. This we got for TE11, and this is cutoff wavelength, how to find that one. And next coming to the same expression for cutoff frequencies, and next again you take some of the problem for related to circular waveguides. This is the problem given. Let's find a circular waveguide, only given radius 2 centimeters, and the value for TE11, and this case T1 means to substitute m is equal to 1 and n is equal to 1, and this is the expression. We can substitute our values here, and we got the cutoff frequency. Similarly for TM, again you take the same relation, we got the values for how much amount of cutoff frequency of that particular waveguide. And next up this the first part of our second unit, but maximum this is already covered in our first unit, and we can't expect any question from this part our examination from second unit, or otherwise some rare cases asking the solution of wave equations either TE or TM. But this is also not asking, already we observed in our first unit, but that's why maximum they can ask in the question. But they asking the question from our examination according to our second unit is only the next topic is cavity resonators. And this cavity resonators means this is just extension of your waveguides, but in our waveguides we are using two coordinates only in the form of our expression sine m pi by a into x, sine n pi by b into y. But here in circular cavity resonator we can add in the third parameter, and when we are adding the third parameter just extend the same. But again you take for rectangular cavity type, cylindrical cavity type. Rectangular cavity type are calculated using EX, EY, EZ, and circular cavity resonators are calculated using E rho, E5, EZ. For that case, you can observe this is the already we can solve in our class the equations, microstrip lines, and how we can solve all the expression for our system. We can observe here same coordinate system. And the next one, microstrip lines, and this is the extension of our microstrip antenna. What we observed for our microstrip antenna, and it consists of substrate, pads, and ground plane, and the front plane is substrate, and above the substrate we observed as a patch, and bottom side is a ground plane, and these are designed starting at gigahertz frequencies. This is what we learn in our antenna analysis, And that antenna analysis, we know already what is meant by microstrip line. We have different types of microstrip lines is there, rectangular microstrip line and circular elliptical shapes is there. But you are using of your microstrip line in waveguide analysis, how we can analyze. But we observed in our waveguide, transverse electromagnetic waves are not propagated. Only transverse electric waves and transverse magnetic waves are propagated. Why the transverse electromagnetic waves are not propagated? Means impossibility of transverse electromagnetic waves. When the propagation of transverse electromagnetic wave means the field components along z direction is equal to 0. That's why the electric field along the z component, the magnetic field along the z component Ez and Hz equal to 0. When we are substituting the values of Ez and Hz is equal to 0, what about the field components we got from our rectangular waveguides of Ex, Ey, Ez, Hx, Hy, Hz? Within that field component, you substitute your values of Ez and Hz equal to 0. All the field components are 0. There is no possibility Ex equal to 0, Ey is equal to 0, Ez equal to 0, Hx equal to 0, Hy is equal to 0, Hz is equal to 0. This is already we observed in our class when substituting for drawing sketches. And similarly, we go for circular waveguides. Again, transverse electric waves, there is no impossibility. Again, you substitute of that components of Ez and Hz equal to 0. In the field components of E rho, E phi, Ez, H rho, H phi, Hz, again all field components are vanished. That's why there is no possibility for transverse electric waves in rectangular waveguide and circular waveguides. But here there is a probability for we are transmitting of microstrip lines. We are using of transverse electromagnetic waves. That's why we can extend here in the microstrip lines, as well as this is called not 100% of propagation of transverse electromagnetic waves, but a quasi means some part of the transverse electromagnetic waves are only transmitted in microstrip lines. That's why most of the cases we are designing of our Wi-Fi connection and WLAN connection we are using for design of microstrip patch antennas. But our mobile phone also, whatever the mobile phone we are using, but each and every mobile phone has some inbuilt antenna is there, and some of the cases depending upon the company, they can use the microstrip antennas for using for inside that phones for to build off compact size. Your antenna is very compact and it is inserted in phones. But we are observed in our nowadays a small there is a lot of features for each and every phone, but we are preferring for compact size, a lightweight slim phones is there. But nowadays the antenna engineers has main focus on its compactness. But when the size of the antenna is reducing, but the antenna designer has a very big challenge to design within that compact, within that small type of phones, a slim type of phones. So you have to design your slim antenna, and this is one of the important criteria for present day. The antenna engineers they take a big challenge for whatever the antennas they are designing for different companies like whatever the familiar companies, Apple or anything is there. Whatever the phone nowadays available in different countries, companies different countries releasing the number of phones depending upon the features, special features. The antenna is a very big issue to insert in that particular antenna. But you are designing of that device of your mobile phone very slim, but within that mobile phone you have to insert of your antenna is also you can take as a compact. That's why nowadays it becomes as a big challenge for antenna engineers. They can design for compact size as well as multiple applications, but not only for the antenna design for only mobile phones, but this is also used for the same antenna for multiple application for the at different frequencies. I'm using for WLAN application, wireless LAN application, or Bluetooth application. And suppose you take a mobile phone, this mobile phone has some of the features, Wi-Fi is there, sharing option is there, and so many options is there. But we are designed for your antenna what inserted in our mobile phone. You design only for Wi-Fi. There is no working of Bluetooth. It is not useful. But it is applying for multiple operations, not only compact size. What about the antenna you are designing? This is useful for multiple application. It is a very good one. That's why it is also major impact. And for that case, I am changing some of the modification in waveguide. What about the microstrip line I am using? And for that microstrip line, I am adding with waveguides. How we can change off this quality factor of all those things. And then next you can observe one of the big major issue for microstrip lines we are using for different application. Already I am saying at the starting of the class is a radiation problem. But we can observe we have using in our nowadays present days the mobile phone increasing is in society is a very big one. Means number of phones are using. When using of this phones working, we are using the number of towers also. When we are using the number of towers, we are creating the more radiation. And this is also very big issue. And I told for one of the application for these issues are eliminating by using of EMC or ECCM applications. I told for electromagnetic interference. And for that case, we can possibility is there. But one of the main big issue of this problem is radiation losses, and how we can overcome of these radiation losses when using of waveguide. But using without a waveguide, but we got a problem of more radiation. But using of my waveguide analysis, but I am not saying 100%, but 70 to 80% I am removing of these radiation losses. In that case, we can observe for this is for microstrip line. This is general representation of microstrip line. Already told this is height of the patch, relative permittivity of the patch, the thickness of the patch, and width of the patch. Thickness means where we are putting up our mobile phones. The thickness is very important for design. And in this case, we are find out some of the equation for wave impedance. But this wave impedance should be equal to a characteristic impedance of 50 ohms. And this is already we learned in our transmission line why we are equating to 50 ohm transmission line. This is one of the big issue. You have to show the characteristic impedance should be equal to 50 ohms. And this I will show from my design. And then we are calculating some of the parameters. Already we observed in class. I'm skipping off this one. We calculate dielectric constants for different cases. And this is the characteristic impedance. And this is the final equation is required for microstrip line with the dielectric h by omega square root of mu by epsilon. And this is taken from our relation 377 intrinsic ohms and relative permittivity of the substrate, the height and width of the substrate. And this we can take from our analysis, circular waveguides and microstrip lines. But this case, we can expect the question from our second unit, maximum from cavity resonators. This is cavity resonators. They can asking derive the field equations for rectangular cavity resonator. Means you take our analysis what I am showing in our PDF file, what we observed in our class. I draw a graph for a circular cylindrical coordinate system. I am placing all the coordinates of Ex, Ey, Ez, E rho, E phi, Ez, H rho, H phi, Hz, and how to solve the components of E rho is equal to C naught of rho sin m pi by A into X cos n pi by B into Y. And another component is both are cos, next term will become sin p pi by d into z. Another component. Previous case we are using only xyz component. Suppose we take off E rho means E rho naught of rho cos m pi by A cos sin n pi by B. And this is for rectangular coordinate system. We are using x and y coordinates. But we write our expression Ex is equal to some C into sin m pi by A into X sin n pi by B into Y. But coming to rectangular, we are adding another third coordinate, and for that case the expression will become, suppose Ez solution equal C sin m pi by A into X sin n pi by B into Y, and both are sin means the next component will become cos p pi by D into Z direction. This is the only term changing, remaining all are same. And similarly written for cylindrical, E rho, E phi, Ez, H rho, H phi, Hz in terms of rho phi Z. But we can expect 100% the question from second unit from part A related to cavity resonator. They can asking derive the expression for derive the wave equation for rectangular cavity resonator, or derive the wave equation for cylindrical cavity resonators. You can remember, this is already told in our class. Read out the previous question papers from the last 3 or 4 years in classroom. You can check and you can take the classroom also. But we can expect maximum this question from this 100% or 90% we can expect. And coming to the next essay question from part B, they can ask him from microstrip line. Explain about microstrip line waveguide. Otherwise related to quality factor, define quality factor, and we can take for 3 different cases: k equal to 1, k less than 1, k greater than 1, critical coupling, under coupling, over coupling. We can draw a graph how the frequency versus coupling. And these are the 2 questions expected from the second unit. One from cavity resonators and second from microstrip lines. But we are going to study just to go for our circular waveguides also. But maximum we can refer the last 3 or 4 year question paper. Maximum. Why we are not giving that circular waveguides means already they can solutions are already observed in our first unit of rectangular waveguide. But the same procedure, but the difference is coordinate system. That's why they can ask not asking the question, but only asking these cavity resonators and microstrip lines. But we can more concentrate related to second unit these 2 topics. But already I told in class also, the first 3 units are entire mathematical parts, but you want to got the full marks. You write expressions, you know the final equation solution. You write that final equation. In between, you write the what I told for step-by-step analysis. You follow that step-by-step analysis. We got full marks. But the last 3 units are completely based on some theory and 1 or 2 equations. But it is not a difficult mathematical equations. One you follow 1 or 2 times practice, it is very easy. Next, this is the second unit completion. Coming to the third unit, microwave tubes, and this is the entire third and fourth unit. The name itself microwave tubes, and we observed we draw in the class one of the chart the total microwave tubes what using in real-time application as well as theoretical application. The sense means, but our educational institutes only we are using for some type of tubes. But we go for industries, they can using a number of type of microwave tubes for especially the design of radars as well as satellites. For that case, most of the case we are using of our microwave tubes. For our educational institutes, using only the basic types of 2 cavity Klystron amplifier, and next we can take for a reflex Klystron oscillator. In our laboratory purpose also, we done the experiments based on that two operations. Only we can whatever the experiments we done. Next, coming to the microwave tubes, and these microwave tubes using for our education institute, what we done in our laboratory purpose. What about the different types of experiments done for different cases, and these are all basic cases. And next we can take for our real-time application where we are using of our RF industry and the radio frequency industry, implementing of different types of cases, the systems for real-time where we are using of this microwave frequency. That frequency tubes are different. And this case we are going to discuss in our third unit. The first one is limitation and lifespan of conventional tubes at microwave frequencies, and then reentrant cavities. What is meant by reentrant cavities? Next, microwave tubes. What are the classification of microwave tubes? And this is 2 cavity and multi-cavity Klystron amplifiers. And next, next electronic admittance, how we are using of this electronic admittance. The first one, coming to the introduction, why we are using of these microwave solid state devices. For that case, we can observe at microwave frequencies, the size of the electronic devices becomes very much large to generation of microwave energy, and that generation of microwave energy, it requires as a less power handling capability and increasing noise levels. And here, before discussing about these microwave tubes, but we know for our basic electronic devices, how we are operating of these basic electronic devices for when we are using for our basic transistors in the form of BJTs, FETs, MOSFETs. And these are all operated in terms of up to megahertz frequencies, but that devices has not the capability for to range take the frequencies of gigahertz frequencies. But our microwave tubes required as a higher amount of frequency ranges. How to implement of that particular system, and for that case, we can observe the size of the devices will become large. That's why we write at microwave frequencies, the size of the electronic devices required for generation of microwave energy becomes smaller and smaller, and this results less power handling capability as well as increased noise levels. For that case, what are the different types of tubes we are using for our microwave devices? For that case, the tubes in the form of transistors, and the tubes in the form of tetrodes, and the tubes is in the form of pentodes. And these are all the available tubes to operate at microwave frequencies for using of our microwave designs. And for that case, these are the tubes we listed, and we consider the frequency from the range from 300 to 3000 megahertz. This is a conventional tubes. It is very difficult. And this conventional 3000 megahertz means up to we take the maximum in terms of converted gigahertz, and this will become 0.3 gigahertz. But the range of frequency for our microwave is 1 gigahertz to 1000 gigahertz. At that frequencies, we cannot implementing of our system, and more than 1 gigahertz we can implementing. And for that case, we are using of our conventional devices, our basic devices. What are the limitations? That we can observe in our first topic in our first unit, third unit, and that one is limitations and losses of conventional tubes at microwave frequencies. The first one is inter-electrode capacitance effects, and this is written in the form of mathematically XC is equal 1 by 2 pi FC, and when the value of frequencies increases, XC is decreases. And coming to lead inductance effect, we write the expression is XL is equal to 2 pi FL. When length of the conductor is increases, the frequency is also increases, and this is observed in our lead inductance effect. And transit time effect means this is calculated by using the expression of tau z, and in terms of omega by g. When this case we can find out the time, how much amount of time. Next, another important parameter is gain bandwidth, how much amount of bandwidth is there, and this bandwidth is a product limitation, and this can be evaluated the one of the limitation. Next, again, I are using of microwave tubes. Again, we got as a sum of the loss, and here we can observe the RF losses. RF means radio frequency losses, and effect due to radiation. And this means radiation means when we are propagating of that electromagnetic wave within that particular tube, we can observe the radiation of skin effect, and we know the expression of the skin effect del means 1 by square root of pi f mu sigma, and this skin effect depending upon the conductivity and permeability. And next, another one is a dielectric and these conducting losses. But these are all the basic limitations and losses we are going to observe using at microwave frequencies. And this is one of the question asking from part A, either 2 marks, 3 marks question. Most of the case you can observe your previous question papers. Write the limitations and losses of conventional tubes, or write any 3 or 4 limitation and losses of conventional tubes at microwave frequencies. But we can expect 100% from this part. They can asking from part A. You write learning some we have 5 or 6 limitations is there, but they can ask any 2 or 3. But you learn any 2 or 3, you can write from part A question. Next, coming to second part, and this entire based on microwave tubes. And according to our classification, the main purpose of using this microwave tube is the power from DC voltage source supplied to the microwave source of AC, convert to DC to AC. And this case you can observe what is use of electron beam generation, velocity modulation, and conversion of density modulation, transfer of energy, and collection of electrons. And this is already know. You're remembering we draw the two cavity klystron amplifier on the board, and this two cavity klystron amplifier has a input is taken at one side and output is measured at another side, and that's why we call it as a two cavity klystron amplifier. And we go for another second one is reflex klystron, and this reflex klystron means we are measuring both input and output at both one cavity, and that's what we are going to discuss. And these are all the basic definitions related to our microwave tubes, electron beam, velocity modulation, and this exact definition from electrons injected from cathode to anode, how we can inject it. And this case you can observe. And next, conversion of density modulation, velocity modulation to another type of current modulation, and current modulation to velocity modulation. And next, transfer of energy, how the transfer of energy is transmitted using of electrons of all this energy. And next, collection of electrons, and this collection of electrons means we are transmitting of electromagnetic wave at input side, and I will explain the next concept in the form of puncture cavity and catcher cavity, and how we can collect the electrons at the output side. This will become collection of electrons. And this is a klystron tube, and we have two different types of klystron type tubes is there. One is two cavity klystron amplifier, and two cavities means we are using for input separately, output per separately. And reflex klystron oscillator, and this reflex klystron oscillator means for input and output both are same. Next, the use of two cavity klystron used in real-time application is amplifiers, microwave amplifiers, and to convert one type of modulation into another type of modulation. And I take for two cavity klystron amplifier, we are going to operate the operation input cavity in the form of buncher, and output cavity in terms of catcher. Bunch means we take a number of electrons collection from input side to output side. First we can bunch, and then at the receiver side we are collecting. And this case we go for actual concept what we observed in our theoretical class, and this is the diagram I drawn on the board. This is a two cavity klystron amplifier. This is first electron gun, and next this is one input radio frequency input, and this is another output radio frequency output. Input is applying here, output is measured here, and for that input entering I am using a coaxial loop, and output I am again using for measuring of RF output is a coaxial loop. And then here you can observe this is for gap A and this is for gap B, and these are the some of the devices called focusing electrodes. And here the electrons are moving from a radio frequency signal means electromagnetic waves means the electrons in the form moving from input side to output side means cathode to anode and anode to cathode. And here I am giving a radio frequency signal here, and these radio frequency signals, the number of electrons are moving from input side to output side, and individual electrons are not moving from input side to output side at microwave frequencies. When the individual electrons are moving from input side to output side is very difficulty, and the signal will be lost and signal will be overlapping. But that case what about the electromagnetic signal, the radio frequency signal we are applying at the input, and these are going from input side to output side in the form of a bunches that we call as electron bunch. Suppose I take this one, 1 2 3 4 5 electrons form a bunch, and these 5 electrons are moving from input side to output side, from cathode to anode or anode to cathode. Input side we are transmitting of that bunches, we call a just you take a number of electrons, and these electrons are within the cavity gap form a bunch, and that is called a buncher cavity. And these electrons are again collecting at output side again in the form of catcher, and this is called catcher. That's why we call it as catcher cavity. And this catcher collect the electrons and again sending from the output side individually. Suppose these are electrons, and for that case we are applying a voltage here, and based on this entire operation it is working. And this case we can observe the one of the operation for early electron, late electrons, and this is the diagram. The physical diagram, we are applying for radio frequency signal. An AC input signal is applying in the form of positive half cycle. This is 0 and this negative half cycle. And this positive half cycle means here you can got as a maximum amplitude and this is a minimum amplitude. And this is called late electron and this is called reference electron and this is called early electron. And by using of this process, the electrons are moving from input side to output side. And similarly, we find for mathematical equation for what about the input efficiency and output efficiency. And by using of this basic voltage expression, at equilibrium condition, static energy should be equal to kinetic energy and half mv square should be equal to EV. By using of this expression, we can solve the velocity of modulation V naught expression equal square root of 2 EV naught by m. And this is the signal I am applying for two cavity crystal in the form of V1 sin omega t. And the entire process using the mathematical expression, we are equating static energy and kinetic energy, and we can solve the efficiency finally. And this is the final expression we can solve in our class. The entire equations available in our notes. And finally, we got how much efficiency. And this is called how to find efficiency means the ratio of output power to the input power. Input power means applying at the input at a buncher and output is measured at catcher cavity. We got these two ratios, so we got the total efficiency is approximately equal to 58% for two cavity. But again, we are using for the same process what we done for two cavity Klystron amplifier. Similarly, we are implementing for reflex Klystron oscillator, but the difference is in reflex Klystron oscillator we are measured both input and output using a single cavity device. And in that case, we can observe the diagram for that one. This is real time. We can observe from the textbook diagrams. We can take from application diagram. And these are all the performance characteristics of our two cavity. Frequency ranging from 250 megahertz to 100 gigahertz. And next power gain, bandwidth, noise figure, theoretical efficiency. But what we done the analysis, how we are moving of the electrons using coming to the applications. The two cavity Klystron amplifier is used in UHF television transmitter. Suppose we are using the transmit the signals in UHF television. We are using of our two cavity Klystron amplifier. Now next troposphere scatter transmitters, and for satellite communication ground stations. And ground station means we are using one transmitter and one receiver. We are using of 8 gigahertz or 12 gigahertz transponders, transmitting from using of line of sight propagation. We can operate of this device. And next radar transmitters, and using of we can manufacture of one of the devices of radar. Also we are using for our two cavity Klystron amplifier. Then coming to the last one, the last topic, reflex Klystron. And again, this is the one of the microwave tube for our entire microwave lab done with the help of this reflex Klystron. Means what about the inputs? Means I want to find waveguide parameters. I want to find out the waveguide parameters for rectangular waveguide, circular waveguide. What we learn: guide wavelength, phase velocity, group velocity, impedances. Next, we go for measurement of VSWR, measurement of frequency, and for what about the parameters we want to measure with in our microwave lab. We are using definitely the input is taken from our reflex Klystron. That's why this is the one of the device, and we can observe in our laboratory the physical view of that reflex Klystron. First, why we go for this reflex Klystron? What are the advantages coming compared to our two cavity? First one is it is a low power microwave oscillator and works on again velocity and current modulation, same as previously, but it is operated for low power microwave oscillator. And next, another device of this one is it is operated with a repeller to repeller electrons and a reflector and back to back of giving feedback system. And it can consist of cathode, electron beam is injected from focusing electron, and this is also used for narrow beam transmission. And next, this is also applying for beam of velocity modulation for in the form of different types of system from moving electrons from forward journey or return journey is taken from velocity modulation to current modulation. And for that case, we go for what we observed in our classroom, the diagram for the graphical representation or schematic diagram for reflex Klystron, and this is our reflex Klystron diagram. We draw in our classroom, and again you take here. Previously, we are using only repeller voltage, For that case, the diagram of two cavity klystron amplifier shows input side we take from cathode to anode, and input cavity and output cavity, but input is applying separately and output is applying separately, but using a Rippler voltage VR only. But in our using of our reflex klystron oscillator, we are adding anode voltage. This is a negative anode voltage we are applying, and this is top one is applying for anode cavity, and again radio frequency signal input and output are measured here by using of coaxial cable. And when we are varying of this voltage using of VR and VA, again we are sending from the electrons from cathode to anode, anode to cathode in the form of reference electron, late electrons, and this is the diagram we draw in our class. We take a radio frequency signal as input and take as a maximum electric field, reference electron, maximum negative field. Again, this is one complete cycle, next complete cycle we draw in class. Early electron, late electron, reference electron. This is E represents early electron, ER means reference electron, and EL means late electron. And after forming of all these in the form of a one electron bench, again we complete of that one complete cycle. Again go to the next RF signal, radio frequency signal, again positive, 0, negative, and again we can form another bunch. And this is also continuously done from moving from electrons from input side to output side in the form of bunches, both input and output measured at same place. But again using the mathematical analysis, for that mathematical analysis, again we find input power and output power using our equation. This is already we saw in our classroom. This is characteristics how we can draw the power. One is for output anode voltage versus Rippler voltage by varying of anode voltage for different modes. And next, this is the output we drawn for power and frequency characteristics. Along x-axis is Rippler voltage, one axis frequency, one axis voltage. You can draw from different types of modes. And next, this is mathematical analysis. Again, we are taking from at equilibrium condition, static energy should be equal to kinetic energy. We take from our basic equation V0 equals square root of 2 EV by M. And your signal, your RF voltage signal is V1 is equal to sin omega t. Again, you can, this is already told for according to equilibrium condition. And this is your signal transmitted. And then we can solve. Again, you find for different time constants, early electron, late electron, reference electrons. For different time constants, we are calculating the efficiency. For the DC power, AC power, and efficiency, output efficiency means the ratio of AC power to the DC power. And I am taking value of AC power is this expression and DC power is this expression. I am substituting all those values, and we got according to our function table. And finally, I got the efficiency of two cavity reflex klystron oscillator is 22.78%. And this is for theoretical approach. What I draw the diagram for reflex klystron oscillator, and I am considering it an equilibrium condition when transmitting of radio frequency signal based on the operations of or process of early electrons, late electrons, and reference electrons. I am developing some of the mathematical equations, the power set input side as well as power set output side, and in the form of AC powers and DC powers. And I take the ratios of those two powers substituted here, and these are all theoretical analysis what I take from a mathematical background. I got the efficiency should be approximately equal 22.78%. But I go for the same thing I am implemented in practical approach. In a laboratory purpose, I am doing the same procedure, but we can observe, however, in practical applications in our labs or any industrial application for using for some of the application of radar or satellite anything. And we got the efficiencies are we got approximately 20%. And this is the case we can observe for our system. And the general expression for representation for each time mode is T is equal to n plus 1/4 mode of the system where varying of the different values. And this is the representation of our total two cavity klystron amplifiers and multi cavity reflex klystron oscillators. What is the operation and how we are implemented in our class, the operation, circuit operation, and output characteristics, how to draw the anode voltage versus Rippler voltage, one graph, and another graph is your voltages versus along y-axis is frequency as well as your powers. How much amount of power is required for different time modes of operation. But this is the graphical diagrams I'm taking from the textbook. This is a diagram for reflex piston, and this is for working operation, and this is also our bunching process. What I told for the diagram drawn for our PDF, what we observed in our classroom, and this is the diagram as it is, same diagram. And next here the modes representation is n plus 3 by 4, where varying of n is equal 1, 2, 3, 4. These are called 1, 3 by 4. This is already represented in our class. From the representation of 1, 3 by 4 means 1 negative half cycle, 1 positive half cycle, again 1 negative half cycle, means 1 complete cycle. And this is called 3/4 mode, and this is called 1 complete cycle mode. But this is already we observed in our class notes also for the examples of 1, 3 by 4, 2, 3 by 4, how we can represent it. And then the diagrams, early electron, late electron, what we can explain. And then finally, the last one is performance characteristics. But compared to our previous devices, what we considered of our compared to two cavity Klystron amplifier, I am using a reflex Klystron oscillator. What about the frequency range? Means suppose you want to design your two cavity Klystron reflex Klystron oscillator, the frequency range is operated from 4 to 200 gigahertz. The output power I observed for that particular device is 1 milliwatt power to 2.5 watt of power observed, and the tuning ranges are this is operated, we take from 5 gigahertz. I am using 5 gigahertz frequency. The power is output power is 2 watts. I am using a 30 gigahertz. You can observe the power is 10 milliwatts. And already we are deriving theoretical part. The theoretical efficiency for reflex Klystron oscillator is 22.78%. And we go for the practical application. We go for laboratories or industrial. We can check using of that components, using of that procedure. What about the procedure is there? We got the efficiency is 20%, but the range taken from 10% to 20%. Next, finally come to the application. But whatever the device we are using, finally our conclusion is where we are using, what is the use. But whatever the society, we take anything, any device or any new component, first we can take where we have use of the device. That is main important. And then next we go for the cost, and then it is harmful to society or not, we can check. That case I go for the applications. And coming to the applications of these reflex Klystron oscillators are using in our radar receivers, and I want to use for the particular radar is in the form of MTA radar or CW radar or FMCW radar. You have different types is there, and from that type of devices, the complete radar is not a single, it is a combination of components. Within that combination of components are required one of the component of our reflex Klystron oscillator. And next, another application can be used as a local oscillator in microwave receiver circuits, and we have available microwave receiver circuits. This reflex Klystron can be used as a local oscillator, but we can observe in our analog communication or a digital communication system, we are using some of the local oscillators in the form of IF amplifier, RF amplifiers. Similarly, in our microwave devices of these reflex Klystron oscillator, also we can take one of the local oscillator in microwave frequencies. And next, it can be used as a signal source in microwave generator of variable frequency. And the meaning of this one means I want to find out any waveguide components. Definitely, I want to require the device of reflex Klystron oscillator. But using of that reflex Klystron oscillator, I am generating some signal, and this signal is transmitted through a microwave bench setup. And what about the input taken from radio frequency signal from reflex Klystron oscillator? This is transmitted to a microwave bench setup, taking off some of the components. And at the output side means after this slotted section, we are connecting of that device, different types of waveguide components or multi-port junctions or anything, we can find out that parameters. That's why one of the using of a signal source, the input source for reflex Klystron oscillator for microwave lab experiments. And finally, we can use it as a pump oscillator in parametric amplifiers. And we know different types of amplifiers is no, but according to our microwave, we can using of helix traveling waves too. For all that case, we are using our parametric amplifier. And for that parametric amplifier, so we can using our reflex klystron oscillator is a pump oscillator in parametric amplifier. But this is a one we can observe in this unit. Mainly focus 3 topics. The syllabus we can. One is the limitations and losses of conventional tube at microwaves. But whatever the losses and the limitations which are required to operate of our microwave tubes, frequency from 1 GHz to maximum 1000 GHz. But this is asking for, I told already, for part A question from 2 or 3 marks, you can refer. And coming to SCA question, sometimes they have 2 operations is there. One is 2 cavity klystron and multi cavity reflex klystron oscillator. And they cannot asking complete question. They can asking for a question from only operation. Explain construction and operation of 2 cavity klystron amplifier. Means you write first the diagram, construction diagram, and then you draw the characteristics. Means how the electrons are moving from the 3 types: early electron, late electrons, and reference electron from input to output side. We draw a graph while considering a radio frequency signal. Just you have to explain how to connect off your 2 cavity amplifier circuit diagram, and then the operation performance. Just you have write only for explain circuit and operation. But otherwise they can asking explain the mathematical analysis of 2 cavity klystron amplifier. Means your mathematical analysis means you draw a graph separately, one side input cavity and other side output cavity, and using of the mathematical expression for at different times, and we can find out AC power and DC power, the ratio of those two. We find efficiency for 2 cavity klystron amplifier approximately 58%. That how to prove, but not required from starting onwards. They can ask him separately the question like this. Otherwise, they can ask him directly prove that the efficiency of 2 cavity klystron amplifier is 58%, 57.37% like this. But you can take again same procedure what I am saying, you can completely write. But asking that question separately, this question separately, but the 2 questions total 1 concept. But we can expect 90% that belongs to that question. Otherwise, the next topic in the form of reflex klystron oscillator, again same. The question asking from that one is explain the operation, construction and operation of reflex klystron oscillator. Again, you construct the circuit and explain the operation, how the electrons are moving from input side to output side. But this case we are adding additionally anode voltage, but only repeller voltage. But previous case we are using only anode voltage for 2 cavity. But in our reflex klystron amplifier we are using the repeller voltage as well as anode voltage. But how the electrons are moving from input side to output side, we can explain clearly. And from take a radio frequency signal, and then next you take from mathematical analysis, and again you go for the mathematical analysis. Again you take the diagram and explain for again AC power, DC power, and finally how to prove the expression of your efficiency should be called what we take out of that 50%. But theoretically we can observe, but again they can ask the question from separately, from mathematical analysis separately, and circuit construction operation separately. But maximum we can take in the form of 5, total 5 number of questions. 1 question from limitation and losses from part A, and part B. Coming to part B, 4 questions you have to read out. But I already told in our your classroom, I am read out the questions asking from previous question papers, these type of questions. But we must concentrate on that 4 questions. And this is our 3rd unit. But totally we can take from 10 or 15 questions. Most refer for all the questions. That case, I told for each and every unit what are the short questions asking, what are the essay questions asking, and you must concentrate on them. That questions maximum what felt difficulty to pass the subjects. Take what are the questions I am saying. You can prepare that one. It is very easy to pass the subject. There is no difficulty. But one how to practice the equation for each and every case. The final outcome for either circular waveguide or rectangular waveguide, the final solution is same. But using the coordinate system is different. once you learn one equation, we are changing only the equations by order depending upon which wave you are propagating. But there is no difficulty. But you have to attempt the question. These are all the direct questions. So you refer any question papers from last 3 years. You can observe also. I told in the class the questions are repeated. You can check. And then you have to practice the problems based on what I told in our classroom. The notes is there. These problems are enough. And again, my suggestion for what are the questions related to problems regarding to this subject. What is our standard textbook is there, Samuel Y. Leo, maximum 100%. What is the solved problems is there in our that textbook, they can given as it is. But you have to practice the problems related to these first and second units. Maximum you go for that textbook, what are the questions is there. This is already solved in our class notes. Otherwise, you have to require any number of problems, you go for that textbook. This is the 3 units, first, second, and third units. Have any doubt regarding to these topics or any material is required? Mail to my mail ID. Okay, thank you to all for your listening. Thank you to all. Any questions? Anybody, any questions? Hello? Any doubts is there? Otherwise, I'm stopping. Okay, thank you all.